Write a short introduction for Geoffrey Hinton, the subject of this video. Geoffrey Hinton is a University of Toronto professor emeritus who is known as the godfather of AI. He recently left Google so he could more freely discuss the dangers posed by unchecked AI development. We spoke to him in his London home about the technology he helped create, its many benefits, and why he suddenly fears humanity is at risk.
I got a request from the Wall Street Journal. They want me to correct my obituary.
What do you mean?
They want me to correct my obituary.
They've like pre-written it.
They've
right?
pre-written my obituary. I wonder what Mark Twain would have said about that.
So I guess we don't really need an introduction here, so I will just launch right into it. You've recently given a number of interviews in which you've said that digital intelligence that is used by chatbots and other generative AI may be a better kind of intelligence than the biological intelligence that we have. Can you briefly explain what made you come to this conclusion?
So, in a digital computer, it's designed so you can tell it exactly what to do, and it'll do exactly what you tell it. And even when it's learning stuff, two different digital computers can do exactly the same thing with the same learned knowledge. And that means that you could make 10,000 copies of the same knowledge, have them all running on different computers, and whenever one copy learns something, it can communicate it very efficiently to all the other copies. So you can have 10,000 digital agents out there, a kind of hive mind, and they can share knowledge extremely efficiently by just sharing the connection strengths inside the neural nets. And we can't do that. If you learn something and you want to tell me about it, you have to use sentences or pictures, and you can only share a very limited amount of information that way. So it's much, much slower for you to communicate what you've learned to me than it is for these digital intelligences to communicate stuff. And that makes them much better. They can learn a whole lot of stuff between them.
You've said that digital intelligence is immortal and that biological intelligence is mortal. What did you mean by this?
So if I learn some connection strengths in a neural net that's being simulated on digital computers, then if a particular computer dies, those same connection strengths can be used on another computer. And even if all the digital computers died, if you'd stored the connection strength somewhere, you could then just make another digital computer and run the same weights on that other digital computer. But with us, the knowledge that we learn, the connection strengths, are specific to our particular brains. Every brain is a bit different. The neurons in your brain are all a bit different. And you learn so as to make use of all the idiosyncrasies of your particular brain. And so once you've learned connection strengths in your brain, if you told me those connection strengths, they wouldn't do me any good because my brain's different. So the digital computers are immortal because you can run that same knowledge on a different piece of hardware. We're immortal because the hardware and the knowledge are intricately entangled. You can't separate the connection strengths from the particular brain they're running in. And so if the brain dies, the knowledge dies.
Why should we be concerned about digital intelligence taking over from biological intelligence?
Because I think it's much better at sharing what's learned by a whole bunch of different digital agents who all share the same weights, and they just share the updates to the weights. And now they can learn 10,000 different things at the same time. But also, I think the digital intelligence probably has a better learning algorithm than the brain's got. All the attempts to find a learning algorithm in the brain that works as well as the backpropagation algorithm in these digital intelligences, so far those attempts have failed. We haven't found anything that scales up as well to very large systems as the backpropagation algorithm. So I think they've got two advantages. They've probably got a better learning algorithm, and they can share knowledge much more efficiently than biological intelligences can.
At the time when you entered the field, there were two schools of thought on machine intelligence: mainstream and neural nets. Can you describe the difference between these two approaches?
I can sort of caricature it. So there's two different models of what intelligence is all about. And one model is that it's all about reasoning. And the way we reason is by using logic. And so that's what's special about people. And what we should be doing is understanding the kind of logic that we actually use. And that also went with the idea that the knowledge you store is symbolic expressions, so that I can say a sentence to you and you will somehow store that, and then later you'll be able to use it for inferring other sentences. But what's inside your head is something a bit like sentences, but cleaned up. And there's a completely different model of intelligence, which is that it's all about learning the connection strengths in a network of brain cells. And what it's good for is things like perception and motor control, not for reasoning. That reasoning came much, much later, and we're not very good at it. You don't learn to do it till you're quite old. And so reasoning is actually a very bad model of biological intelligence. Biological intelligence is about things like controlling your body and seeing things. And that was a totally different paradigm and had a different idea of what's inside your head. That it's not stored strings of symbols, it's just connection strengths. The symbolic AI view, the crucial question was, what is the form of these symbolic expressions and how do you do the reasoning with them? For the neural net view, the central question was quite different. It was, how do you learn these connection strengths so you can do all these wonderful things? And so learning was always central to the neural net view. For the symbolic view, they said, we'll worry about learning later. First, you have to figure out how the knowledge is represented and how we reason with it. And so these were totally different views. One took its inspiration from logic and one from biology. And for a long time, the people in the logic camp thought taking inspiration from biology was silly. That was a bit strange, since von Neumann and Turing had both thought neural nets were the way to attack intelligence, but unfortunately they both died young.
Can you, at a high level, describe how a neural network works?
I can try. So let's start off by describing how it would work for recognizing objects and images. And let's suppose all we wanted to do was say whether or not there was a bird in the image. And let's suppose the bird's going to be roughly in the middle of the image and the main object of attention. And you have to say, is this a bird or isn't it? So you can think of an image. Let's suppose it's 100 pixels by 100 pixels. That's 10,000 pixels. Each pixel is 3 colors, RGB. So that's 30,000 numbers. And in computational terms, recognizing a bird in an image consists of taking 30,000 numbers and outputting one number that says yes or no, it's a bird. And you could try and write a standard computer program to do that. And people tried for many, many years, and they could never get it to work very well. Like for 50 years, they were trying to do that. Or you could make a multi-layer neural net. And I'll start off by telling you how you would wire up a neural net by hand. So what you'd do is you'd have the pixels, and that would be the bottom level. And then you'd have a layer of feature detectors. And a typical feature detector might have big positive connection strengths coming from a vertical row of pixels and big negative connection strengths coming from a neighboring vertical row of pixels and no connection strengths anywhere else. So if both rows of pixels are bright, it'll get big positive input from here, but also big negative input from there, so it won't do anything. But if these ones are bright, giving it big positive input, and these ones are not bright, so it doesn't get inhibited by these ones, it'll get all excited. It'll say, hey, I found the thing I like, which is bright pixels here and dark pixels here. And that's an edge detector. I just told you how to wire up by hand using positive and negative weights, something that would detect a little vertical edge. So now imagine you have a gazillion of those guys detecting different edges in different locations in the image, in different orientations, and at different scales. That would be your first layer of feature detectors. Now, if I was wiring it by hand, my second layer of feature detectors, I would maybe have a detector that takes two edges that join at a fine angle like this. So it's looking for this edge and this edge. And if they're both active at once, it would say, hey, maybe there's a beak here. It could be all sorts of other things, but it might just be a beak. So you have a feature that's sort of beak-like. You might also, in that layer, have a feature that detects a whole bunch of edges that form a circle. And so you'd have circle detectors and potential beak detectors, as well as lots of other detectors in that layer. But they're detecting slightly more complicated things. And then in the layer above that, you might have something that detects a potential beak in the right spatial relationship to a potential circle, a potential eye, so that it could be the head of a bird. So that would be like your third layer. And maybe if in your third layer you also got something that detected the foot of a bird and the wing of a bird, then maybe in the next layer you could have a bird detector. That if several of those things got active, like, okay, here's a head and there's a wing and there's a foot, it probably is a bird. Okay, so I told you how to wire all those things up by hand, but you'd never be able to do a very good job of it. So instead of wiring it all up by hand, we could imagine trying to learn it all. So I've told you the kind of thing we want to learn, but now I'll tell you how we learn it. And the way we learn it sounds bizarre at first. Instead of wiring in all the connection strengths so you get the detectors you want, you start with random connection strengths, just random numbers on all the connections. And so you put in an image of a bird, and you go forward through these layers of feature detectors, and it just behaves completely randomly. And the bird detector at the output will say 0.5, it's a bird. It's going to say 1 when it's sure it's a bird, and 0 when it's sure it's not a bird. To me, we're going to say about 0.5. And now you can ask the following question. How can I change all those connection strengths in the network? So instead of saying 0.5, it's a bird, let's suppose it is a bird, it says 0.51, it's a bird. So the question you want to ask is, how should I change a particular connection strength so as to make it more likely that it's a bird? And you can figure that out by taking the difference between what you got and what you wanted. So you wanted 1, and you actually got 0.5. You take that difference, and you send that difference backwards through the network, and then you use some calculus, which I won't explain, and you're able to compute for every single connection in the network how much you'd like to make it bigger or smaller in order to make it more likely to say bird. And you adjust all the connection strengths very slightly in the direction that will make it more likely to say bird. Then you show it something that isn't a bird, and now you're going to adjust connection strengths so it's less likely to say that that was a bird. And you just keep going like that with lots of birds and non-birds, and eventually you'll discover that it's discovered all these feature detectors. It'll have discovered beak-like things and eye-like things and things that detect feet and wings and all that stuff. And if you train it on lots of different objects, like 1,000 different categories of object, it'll discover intermediate feature detectors that are very good for recognizing all sorts of things. So the magic is that there's this relatively simple algorithm called backpropagation that takes the error in the output and sends that error backwards through the network and computes for all the connections how you should change them to improve the behavior, and then you change them all a tiny bit, and you just keep going with another example. And surprisingly, that actually works. For many years, people thought that would just get jammed up. It would get stuck somewhere. But no, it doesn't. It actually works very well.
I'm curious, how do neural networks handle language?
Okay, so now you've got the idea of how we train it to recognize a bird. Imagine now that we take a string of words as the input. And the first thing you're going to do is convert a word into an embedding vector. That is, it's a little bunch of numbers that captures the meaning of the word, or is intended to capture the meaning of the word. And so your first layer after the words will be these embedding vectors for each word. And now we're going to have lots of layers of embedding vectors. And as we go up through the network, we're going to make the embedding vectors for a word get better and better because they're going to take into account more and more contextual information. So suppose in this sentence, let's suppose we don't have any capital letters, okay? So suppose in this sentence you have the word may. Well, the most probable meaning of may is that it's a modal, as in he may do that. But obviously there's a completely different meaning of may, which is the month. And so initially, it doesn't know, just looking at the word may, it doesn't know what embedding vector to use. And it'll use a kind of compromise vector, something that's sort of halfway between the embedding vector that represents the modal may and the embedding vector that represents the month may. And then at the next layer, it's going to refine that vector. it's going to make a slightly better vector depending on the context that it got, depending on nearby embedding vectors. So if, for example, nearby there's the embedding vector for June, then it'll refine the one for May to be more like a month and less like a modal. But if there's the embedding vector for wood, it'll make it more like a modal and less like a month. And as you go through the network, it can refine these embedding vectors and make them better and better. And the way we're going to train it is we're going to give it a string of words as input. And we're going to, here will be one way to do it. It's not exactly what's done, but it's easy to understand. For the last word, you just put in a kind of neutral word. You say unknown. And it has a very vague embedding vector that's kind of the average of all the vectors for all words. It doesn't know, right? Now, as you go forward through the network, that last word will be able to be influenced by previous words. And it starts off very vague, but as you go through these layers, it can get more and more precise. And by the time you get to the end of the network, that embedding vector could look like the embedding vector for a particular word or for some combination of words, some average of several words. And you train the network by saying, you go through all these layers, and that last word, you'd like the embedding vector to look like the embedding vector for the word that actually was there in the text. And that's how it predicts the next word. It tries to change this sort of neutral embedding vector into one that is close to the embedding vector for the correct word that appeared in the text. And you take the error, the difference between the embedding vector in the text and the embedding vector it produced, and you propagate that backwards through the network. And it's propagating backwards through the layers, but it's propagating from this word to previous words so that they will have the right influence on this word. And that's the backpropagation algorithm learning to predict the next word.
So despite some of the theoretical breakthroughs in this field, these neural networks didn't work very well for a long time. And why was that?
It was a combination of reasons. So we weren't very good at initializing them. That is, I said you put in random weights and then learn everything. But if you don't carefully decide what kind of random weights, the thing never gets off the ground. So that was a little technical reason why they didn't work very well in deep nets with lots of layers of feature detectors. But the main reason was we didn't have enough compute power and we didn't have enough data. So people were trying to train these nets on relatively small training sets without much compute power. And in that regime, other methods worked better. Neural nets really come into their own when you have a lot of data and a lot of compute power. And then you can use a big neural net, and then it works much better than anything else. And we didn't realize that at the time. So we would occasionally fantasize, well, suppose you had a lot more data and a lot bigger computer, it would work better. But we didn't realize it would work a whole lot better. And so in the 1990s, it was a relatively dead period for neural nets because other methods were working better on small problems. And a lot of people in computer science gave up on neural nets. In psychology, they didn't, because in psychology, they wanted something that was like the brain. And neural nets were clearly more like the brain than symbolic AI. But in computer science, neural nets sort of came into disrepute in the 90s.
So let's fast forward then to another decade, to the 2000s. Was there a moment for you when it became clear that the approach that you'd been pursuing was the one that was going to prevail?
Okay. In 2006, we figured out how to initialize the weights much better by doing unsupervised learning, and then backpropagation worked much better. So it was fairly clear then that backpropagation really was going to work very well. But in 2009, two of my grad students, George Dahl and Abdul Rahman Mohammed, made a much better speech recognizer. Actually, a slightly better speech recognizer, but it was slightly better than the state of the art, using deep neural nets. And then it was fairly clear that this stuff was going somewhere. And all the big speech groups over the next few years switched to using neural nets. And then in 2012, that speech stuff came out in the Android, and suddenly the Android caught up with Siri. It was as good at speech as Siri because it was using neural nets. And in the same year, two others of my graduate students, Ilya Sutskova and Alex Krzyzewski, made a neural net that was very good at recognizing objects and images. And that beat the state of the art by a lot. And so I think it was this combination that it was already working for speech recognition and already in production. The big companies knew that. The public, I don't think, were very well aware of that. But then suddenly it worked much better for computer vision. And that was a turning point. In 2012, when we won the ImageNet competition by a huge margin, we got almost half the errors of the other methods. And it was a public data set, but with a hidden test set, so you couldn't cheat.
So let's just focus a bit on 2012, because you said it was a really pivotal year for this. Can you describe, again at a high level, how AlexNet worked? I take it that might have been named after your graduate student.
That was named after Alex Krzyzewski, because he was a wizard programmer, and he made it work. Ilya helped a lot, but it was mainly Alex's work. So I explained to you, when explaining backprop, how you'd have these layers of feature detectors. And AlexNet was basically that kind of a net, but with 1,000 different object classes and with about 7 layers of feature detectors. And it also used something else that was developed by Yann LeCun, which is convolutional nets. And I'll try and explain those now, because they were very important. Remember how I said you might make a detector for a bird's beak by checking by having 2 lines like that. And if you see those 2 feature detectors, then you make a beak detector. But that would just be for a specific location, right? In a convolutional net, when you make a feature detector for one location, you make the same feature detector for all the locations in the image. So now if it's trained with a beak here, when it's learning, and it really says, I need a beak detector for that, so it learns a feature that detects this beak, it will automatically make copies for all of the other locations in the image. So if now the bird occurs in a different location, it will have the feature detectors to recognize it. So that idea that you copy the feature detectors to every location, that's a convolutional net essentially. And that makes the whole thing generalize much better across position. It can cope now with things changing position because it's got copies of all these feature detectors in every location. And with convolutional nets and multiple layers of features, what Alex did was programmed all that very efficiently on a thing called a graphics processing unit, which was developed for computer graphics, but is like a mini supercomputer. It can do lots and lots of computation in lots of separate processors all at the same time. And so it gave us about a factor of 30 compared with a normal computer. And a factor of 30 is about sort of 10 years progress in computers. So suddenly we could leap 10 years into the future in terms of compute power. And it was very difficult to program these GPU boards. Alex managed to program 2 of them to collaborate, which was even more difficult. And the last ingredient was the ImageNet dataset. So someone called Fei-Fei Li and her collaborators put together a big set of images and then a public competition where you had about 1 million images with 1,000 different kinds of objects. So you had about 1,000 examples of each kind of object. And you had to learn to recognize those objects. And then the test set would be different images, which also contain those objects. And so you'd have to generalize to the different images. And it turned out the best computer vision technique that had been invented up till then was getting like 25% errors. And Alex got 15% errors. And since then, it's gone down to about 3% errors. It's got much better since then. But it was a huge jump. And people in computer vision were extremely surprised. And most of them behaved in a very admirable way, which is they said, hey, we never thought this would work, but hey, it works, so we're going to do that instead of what we were doing. That's what scientists don't usually do. Scientists usually just grow old complaining that this new stuff is nonsense.
And how would you describe the pace of innovation that we've seen in AI since that moment?
It's just got faster and faster. So if you'd asked me in that moment, how long till these neural nets can do machine translation that's better than the state of the art, I'd have said maybe 10 years, Because machine translation is the kind of thing that, if you've got a theory that's all about processing strings of symbols, machine translation is the ideal problem for you, because you have a string of symbols in one language and you have to produce a string of symbols in another language. And the symbolic people thought, well, inside you're just manipulating strings to do that. The neural net people thought you have to take this string of symbols, you have to convert it into these big patterns of neural activity, and then you have to convert it back into symbols at the output. And I was very surprised when it only took a few years for machine translation to be good, and then in another year or two, Google was using it, and it greatly improved the quality of machine translation. Like in languages like Chinese, this is from memory, but there was a gap between how good the computer translation was and how good human translation was, and it just halved that gap overnight. I think it was Chinese that did that. But in a lot of languages, it just made it a lot better. And since then, it's got considerably better since then. But by 2015, it was already working pretty well. And that really surprised me that it only took 3 years.
You say you were surprised at the pace of innovation. What did you think the first time you used a large language model like ChatGPT? Did we surprise you?
I'm just shocked at how good it is. So it gives very coherent answers, and it can do little bits of reasoning. Not very sophisticated reasoning yet, although it'll get much better. So for example, I asked it, this is GPT-4 now, I asked it a puzzle given to me by a symbolic AI guy who thought it wouldn't be able to do it. I actually made the puzzle much harder and it could still do it. And so the puzzle goes like this. The rooms in my house are either white or blue or yellow. Yellow paint fades to white within a year. In 2 years' time, I would like all the rooms to be white. What should I do? And a human being would probably say you should paint the blue rooms white. What GPT-4 said was you should paint the blue rooms yellow, but that works too because the yellow will fade to white. And I don't see how it could do that without understanding the problem. The idea that it's just sort of predicting the next word and using statistics, there's a sense in which that's true, but it's not the sense of statistics that most people understand. From the data, it figures out how to extract the meaning of the sentence, and it uses the meaning of the sentence to predict the next word. It really does understand, and that's quite shocking.
So have you been surprised by the broader reaction, the public reaction to ChatGPT?
Well, given how well it works, I guess the public reaction isn't that surprising. But what's interesting is most people don't say, this doesn't understand. They say, wow, it understood what I said and gave me a coherent answer. What can I use it for? And I think most people are right about that. And of course, it can be used for huge numbers of things. So I know someone who answers letters of complaint for the health service. And he used to spend 25 minutes composing a letter that addresses the problem and so on. Now he just types the problem to GPT-4 and it writes the letter. And then he just looks at the letter and decides if it's okay and sends it out. And that takes him 5 minutes now. So he's now 5 times more efficient. And that's going to happen all over the place. Like paralegals are going to be like that. Programmers are already getting like that. Programmers can be much more efficient if they get assistance from things like GPT-4, because it knows how to program. And you might think it just knows how to program because it's seen a whole lot of programs. So I have a former graduate student who's very smart and a very good programmer. And he did a little experiment, which is, he's called Radford Neal. He took GPT-4 and he defined a new programming language with very unusual syntax. And having defined this programming language, just in text to GPT-4, he then gave it a program and said, what would this do? And it answered correctly. So basically, it could understand the definition of a new programming language and figure out what programs in that language would do. And again, the idea that it's just predicting the next word doesn't make any sense in that context. It had to understand what was going on.
So what do you see as some of the most promising opportunities for this type of AI when it comes to benefiting society?
It's hard to pick one because there's so many. Like, there'll be a huge increase in productivity for any job that involves outputting text. There's all sorts of issues about increasing productivity. In our society, it's not necessarily a good thing to increase productivity because it might make the rich richer and the poor poorer. But in a decent society, just increasing productivity ought to be a good thing. So there'll be things like that. It's wonderful for making predictions. It'll be better at predicting the weather. People don't know by how much yet, but it's already much better at predicting floods. It can predict earthquakes. It can design new nanomaterials. So for things like solar panels, you want to be able to design new nanomaterials, or for superconductivity. I don't know if it's used for superconductivity yet, but it may well be. You'd like that at high temperature. It's really good at designing drugs. That is, finding molecules that will bind to some particular other molecule. DeepMind has used it to create AlphaFold. Now that's not a chatbot, that's just deep learning. But the basic technology of deep learning has pretty much solved the problem of how you figure out from the string of bases in a protein what shape it will adopt. And if you know what shape it adopts, you know its function. The chatbots are just going to be used everywhere, I think.
And we've also talked a lot about healthcare. I mean, you talked about drug discovery, but healthcare is another field that could really benefit.
Yes, both in interpreting medical scans. Like if you take a CAT scan, there's a lot of information in the CAT scan and that isn't being used. And most doctors don't know what the information is. This will be able to get much more out of a CAT scan, as well as being able to compete with doctors at saying what kind of cancer you have or how big it's grown. At present, for example, when a doctor tells you the size of a cancer, you'll get a number like it's 3 centimeters, and a month ago it was 2 centimeters. Now, that's not a very useful number if the thing looks like an octopus, right? A neural net will be able to do much better at understanding the volume of the cancer and how it's changed. So it's going to be tremendous there. And already it's at the level of humans for lots of kinds of scans, and it's going to get better. It's going to be very good for diagnosing diseases. So at present, there's a large number of people die in North America because the doctors misdiagnosed what they had. There's a system that Google's producing called MedPalm2, which has learned to do diagnoses. And it's already, I think it's better than an average doctor now. I'm not quite sure about this because I'm not at Google anymore and it's very recent. But it's certainly comparable with doctors and it's going to get better fast. So wouldn't you like to have a sort of general practitioner, family doctor? You go with some rare disease and you'd love your family doctor to have already seen hundreds of cases of that rare disease. And MedPalm2 is going to be like that. So it's going to be just, in the end, much better at diagnosis.
It sounds like AI will bring many important benefits. But you have expressed concern about the current pace of innovation. Why?
Okay, so for like 50 years, I thought that, well, for 49 years, in order to make digital models better, we needed to make them work more like the brain. So I kept looking at things the brain does and the digital models don't, like rapidly changing connection strengths in a temporary way, and that can make the digital models better. And very recently, I realized that because these digital models have this kind of hive mind where when one agent learns something, all the other agents know it, they might actually already be better than biological intelligence. And so I kind of completely flipped my opinion from the idea it's going to be a long time before they can do everything the brain does. It's going to be 30 to 50 years before they're better than us, which is what I thought for until very recently. A few months ago, I suddenly realized maybe they're already better than us. They're just smaller. And when they get bigger, then they'll be smarter than us. And that was quite scary. It was a sudden change of opinion that instead of being 30 to 50 years, it was 5 years to 20 years, something like that. And so we needed now to take really seriously right now what we're going to do about the issue these things may become smarter than us. it's a time of huge uncertainty and nobody really knows what's going to happen. Maybe things will stall and maybe they won't become smarter than us. But I don't really believe that. I think they're going to be smarter than us. But maybe when they become smarter than us, we'll be able to keep them benevolent and we'll be able to keep them caring much more about people than they care about themselves, unlike people. But maybe not. And so we need to start thinking very hard about those issues. And I'm not an expert on those issues. I'm just an expert on these learning algorithms. And I've suddenly realized these superintelligences may be here quite soon. And I'm just sounding the alarm so that people listen to the experts who've been thinking for a long time about how we might stop them taking control. I want the politicians to listen to those guys rather than say, yeah, they're sort of sci-fi guys. It's never going to happen.
Was there like a particular moment when you had this? You said it was very recent, where you kind of changed your view on it?
I was developing learning algorithms for biological systems that could run in a biological system which didn't use backpropagation. And I couldn't make them work as well as the backpropagation algorithm that we run in these digital systems. And they would work for small networks, but when I scaled it up, the digital ones always scaled up much better than the biological ones. And suddenly I thought it might not be my fault. It might not be that my learning algorithm was just a bad learning algorithm. It might be that these digital systems just are better. And that's when I suddenly changed my mind about how long before we get superintelligence. And then I talked to various former students of mine and former colleagues of mine. And some of them encouraged me to go public with this. Not because I had any solutions that I wanted to recommend. It's not like you can say, burn less carbon and everything will be fine. But because they thought I'm well known in the field, and if I go public by saying superintelligence might be here quite soon, the politicians might start to believe that's a possibility and start listening seriously to the researchers who've been thinking a long time about how we prevent these things from gaining control.
So from your point of view, what role can governments play in helping ensure these AIs are developed in a responsible way?
So there's all sorts of risks other people have talked about a lot, and I don't particularly want to talk about, like they'll take jobs away and increase the gap between the rich and the poor. They will make it impossible to know whether news is fake or real. They will encourage society to divide into two warring camps that don't listen to each other and have completely opposing views. They will build battle robots that are designed to kill people. All of those are well-known risks that I'm not talking about. It's not that I don't think they're important. I think they're probably even more urgent. But lots of other people are talking about those risks. The risk I'm talking about is the risk these things will get smarter than us and eventually take over. And for that risk, there may be something governments can do, because nobody wants that. Well, if you exclude these superintelligences, no people want that. And so all the different governments ought to be able to agree. They ought to be able to work together on preventing that, because it's in their interests. And that's happened before. Even during the Cold War, the US and Russia could work together on trying to prevent there being a global nuclear war, because it was so bad for everybody. And for this existential threat, it should be possible for everybody to work together to limit it, if it's possible to prevent it. I don't know whether it's possible to prevent it, but at least we should be able to get international collaboration on that particular threat, the existential threat of AI taking over. One thing I think should be done is wherever this stuff's being developed, particularly these big chatbots, governments should encourage the companies to put a lot of resources, as these things are getting more and more intelligent, to doing experiments to figure out how to keep them under control. So they should be sort of looking at how these things might try and escape and doing empirical work on that and put a lot of resources into that, because that's the only chance we've got. Before they're super intelligent, we can maybe do experiments and see what's going to go wrong. And I'm strongly of the belief you need empirical data on this. You just can't have philosophers and politicians and legislators making up rules. You need empirical work looking at these things and seeing how they go wrong and seeing how you might control them. And that can only be done by the people developing them. So since you can't stop the development, the best you can do is somehow have governments put a lot of pressure on these companies to put a lot of resources into investigating empirically how to keep them under control when they're not quite as smart as us.
And what do you see as the role of these big technology companies where a lot of this development is happening? Would they do this without that kind of government regulation?
So a lot of the people in the big companies, all the people I know who are senior in the big companies are very worried about this and do put work into that. They're very concerned about it, but they have an obligation to their shareholders. And I think to make big profits, and making big profits, particularly in the short term, doesn't align nicely with putting a lot of effort into making sure it's safe. So you see this in all industries. In the railway industry in the States, having safety devices that tell you when a wheel's locked cost money, and the big rail companies just rather have accidents than do that. Google, which is a big company I know something about, is not quite like that because it understands that it's got a tremendous reputational loss if bad things happen. And that's why Google didn't release these chatbots. It kept them private. It didn't want them out there in the world for people to play with. It wanted to use them to give you better search results or to complete your Gmail for you, but not to give them to people to play with. And it could only be responsible like that until OpenAI and Microsoft put them out there, and then Google had to compete. But the big people in the big companies really care a lot about their reputation and about not having bad effects. But they could maybe be made to care even more about this safety issue by government doing something to insist that they put a lot of work into that. And there's other things that could happen, like it's very hard within a company to have people working on long-term existential threats because they're paid by the company and there's a conflict of interest, which is one of the reasons I left Google. Not because Google did anything wrong, because I just don't want any conflict of interest. One thing the big companies could certainly do is put more money into funding foundations that study these things. And Google, for example, put $300 million into a foundation called Anthropic that is studying these things. They could put a lot more money in.
I'm curious about what advice you would give or what guidance you would give to other researchers in the field, who might be just entering the field right now, and want to make sure that they're advancing the field, but doing it in a responsible way.
Well, one piece of advice I'd give is look at how many people are working on making these things better and how many people are working on preventing them from getting out of control. And you'll see it's like 99 people are working on making them better and one person's working on preventing them getting out of control. So where could you make the most impact? Probably on working, preventing them getting out of control. So that's one piece of advice. The other piece of advice is my general advice for young researchers, which is look for somewhere where you think everybody's doing it wrong and trust your intuition until you figure out why your intuition is incorrect. Trust it and work on alternative ways of doing things when you think everybody else is doing it wrong. And the fact is, either you have good intuitions or you don't. If you've got good intuitions, you should listen to them and follow your intuition and work on that until you discover why it's wrong. If you've got bad intuitions, it doesn't really matter what you do, so you might as well follow your intuitions.
The risks you've described are alarming, but can't you just throw a switch and shut it down? Aren't humans, ultimately, still in control?
It's very tempting to think we could just turn it off. Imagine these things are a lot smarter than us. And remember, they'll have read everything Machiavelli ever wrote. They'll have read every example in the literature of human deception. They'll be real experts at doing human deception because they'll have learned that from us. And they'll be much better than us. They'll be like you manipulating a toddler. You say to your toddler, do you want peas or cauliflower? And your toddler doesn't realize, actually, he doesn't have to have either. He just thinks which he dislikes the most and says he'll have the other one. So if they can manipulate people into pressing buttons and pulling levers. So we have a nice example of Donald Trump. Donald Trump can manipulate people, and so he could invade a building in Washington without ever going there himself. And you didn't have to prevent Donald Trump from doing anything physical. You'd had to prevent him from talking to prevent that. And these are chatbots. So the idea that just with talk they can't do any real damage because it requires people to do the damage. Well, as soon as you can manipulate people, then you can get whatever you like done.
You've spent your career trying to understand how the human brain works and played a critical role in AI development. What's next for you, Geoffrey Hinton?
Okay, so I'm 75 and I've reached the point where I'm not very good at writing programs anymore because I keep forgetting the names of the variables I'm using and things like that. And I do a copy and paste and forget to modify the thing I pasted. And so I've slowed down a lot in programming and it's very irritating. It's extremely irritating not to be as good as you used to be. And I decided a long time ago that when I reached that point, I would become a philosopher. And so I'm going to become a philosopher.